This video is very specifically on evolutionary algorithms and diving into them specifically and kind of explaining how they work, and why you would want to use them. The first place I want to start with this is kind of like a philosophical discussion around evolutionary algorithms themselves and taking a look at the research and the researchers involved in AI, I think is the best first place to start within this, right? So outside of OpenAI, and when researchers leave OpenAI, is kind of like the question I think of within this, right? Like where do they go after that first step, and not just picking on OpenAI, but where do they gravitate towards afterwards? And you see people they go into like if they stay within neural networks, they'll go like towards like transformers alternatives, and then there's like a multitude that are popping up within that arena. I made a video specific on that. And then if they go outside of neural networks, there's a whole bunch of machine learning and AI that falls outside of deep learning and neural networks itself, right? And then so when you get outside of that space, you see to me a like a conglomeration around like the most advanced researchers typically are looking they go towards evolutionary algorithms and swarm algorithms. I'm going to make a philosophical claim here that will maybe be a bit of hearsay up front, but I don't think it is, which is that to me, swarm algorithms and evolutionary algorithms are like A and B. They're the same thing, right? If you look at how a swarm algorithm works, I've constructed many of them myself. You're essentially your particle swarm optimization, right? So you're using an optimization or a fitness function to create the swarm and to update the generations of the swarm, right? Which is exactly the same as evolutionary algorithms work, which we'll come into. Like it's all of the same functions. It's a lot of overlap between setting up the optimization function and setting up the fitness function, which are it's the same thing, right? And so to me, evolutionary algorithms and swarm algorithms, they work essentially the same way, and then they have like under that aspect, they've both been around for a long time, and then they are both now seeing kind of like a resurgence, which if you understand hardware aspects, parallelization of hardware, where we're at with GPUs compared to CPUs, etc. Those are all the reasons why, right? Like especially with evolutionary algorithms and swarm algorithms, like they rely on parallelization, like and to an extreme extent, to a point where we need to go much further than we are currently with like GPUs. Like GPUs are child's play with the amount of parallelization that they can do compared to what an evolutionary algorithm and a swarm algorithm would want. But so with that being said and that philosophical overview, let's dive into the actual functional overview of how evolutionary algorithms work. Before we do that, let me go into this video's sponsor, which there is no actual sponsor for. It's myself. And so this video is sponsored by Rick's AI Cafe, your global cafe for engaging AI discussions, creative exchanges, and professional growth. It's a Discord channel, and by popular demand, a lot of people have been asking for me to create Discord specifically around and to encourage AI discussions and an AI community. So I have created it for the community. If you want to check it out, I'll leave a link to the Discord in the description for this video. And then so with that said, diving specifically into evolutionary algorithms themselves, evolutionary algorithms are a type of optimization algorithm inspired by biological evolution. They work by simulating a population of individuals, each representing a potential solution to a problem. So here's a breakdown of the core concepts. One, you have individuals. An individual is a single candidate solution. It has a genome, which is its characteristics, and a fitness, how good a solution it is. The fitness function is very important, right? Fitness replaces your loss function, population. A population is a collection of individuals. And then so over time, you evolve the population by evolving the individuals. Three, your fitness function, which is your way to measure how good each individual is at solving the problem. Higher fitness is better, and that's how you evolve over time. Selection, choosing individuals to be parents for the next generation. Fitter individuals are more likely to be selected. Crossover, which is recombination, combining the genomes of two parents to create offspring or new individuals. So it's a probabilistic crossover, just like it would be within like normal biology, right? And these are all represented by numbers. So let's say that you have an individual who's a zero point 0.4 and an individual who's a 0.6, and then they come together, and then the crossover and the recombination and the next generation of that could be a 0.5, or it could be a 0.4, or it could be 0.6. It's probabilistic, right? And then so mutation, randomly changing some parts of an individual's genome, and this introduces new genetic material into the population. And then so within that same example, there's a small chance that it could be a 2, like or a 1, right? Like because a mutation could happen. And then so generation, a single cycle of selection, crossover, and mutation. The population evolves over many generations. And elitism, copying the very best individuals directly to the next generation to avoid losing good solutions. So while there's a small chance that it could be a 2, if 8 is working, then and 8 is like a dominant solution, 8's going to overwhelm 2 or overwhelm anything else. And so basic process of this is actually a lot more simplistic than you would think it would be when it comes to code. You essentially, it's a 4-step process. You initialize the code, so you create a random population of individuals. You evaluate them by calculating the fitness function of each individual. Then you repeat this over and over again for many generations. Select the parents, do your crossover analysis, mutate, evaluate, replace, and that's it. And then you analyze your results. So after many generations, the population should contain individuals with high fitness, right? And then you get your answer, kind of. And then this code implements a simple, and the code that we're going to look at here implements a simple genetic algorithm, a specific type of evolutionary algorithm. It's used here to solve the max ones problem. So finding a binary string with the maximum number of ones, but the framework's general, and we're going to look at a very unique problem after this one. So essentially, within our code, we set up our individuals and our all of the individuals, the mutations, the frameworks, the genetics, everything that needs to go in. We program it all, right? You're there was an interesting article that came out a few days ago where they actually discovered like a prototype to DNA, right? There's like a there was like a proto DNA before DNA, and so to me, like it's. I'm not saying that code is DNA and along that lines, right? But it's you're programming like along and utilizing the code to stimulate DNA. So you have to like program everything, every aspect of that, right? So you have a lot of classes and functions that you need to define within that, and then so that's all you're just doing is just defining like every single class and function that would need to go into pure evolution, essentially. And then so that's all the concepts that we talked about, right? So at the top, so you have to input all of your arguments. So your individuals, population size, genome length, mutation rate, crossover rate, generations, selection method, tournament size, and elitism count. All of this is programmed, right? And then so you can change and you can adjust these, and these are all parameters that you input, and then they mutate based off of this. But so you need to input your initial math and your initial values for this, exactly how the parents are going to be selected, what happens, your mutation rate for the parents. Like you're not hard coding what happens, but you need to hard code the initial conditions, right? And then so the initial conditions and the initial rules that and the full rules that evolution in this instance needs to follow, and so it ends up being a lot. Is kind of what I'm trying to point out here, that it gets to when you get to like just a genetic algorithm, right? And then the end result is just these are your arguments, but like the rest of it is literally all of this is just the math in support of these arguments, like and that's so, and then the rest is evolution. And then so as you can see here, we have our generations, and then we go through generation 1 through 50, and then in this instance, like this binary code example, it ends up solving it a lot quicker than I thought it would, like a whole lot quicker than I thought it would. It solves it within like 5 generations total, and then like we can see here, and then it's we get our like overall best evolved solution, and then it says like it just picks, it says that this one is the best one, like this generation 20. I don't know what makes generation 20 unique in the instance where we're looking at all ones, but there it is, right? So let me show you a much more complex example of this, because so evolutionary algorithms and tying to like biology and DNA and things like that, but you don't have to tie directly to these things. And that's the first thing that I want you to open and expand your mind with this, right? So just because it's an evolutionary algorithm doesn't mean it has to be tied to biology. You can tie it to anything, literally anything. And then so I'm going to tie it right now. We're going to make a salad using evolutionary algorithms, right? And then so we're going to use an evolutionary algorithm to evolve a simple recipe for a salad. This is unconventional. So essentially what I'm going to do is I'm going to take my genome of my recipe, so I'm going to have my ingredients, my quantities, and my instructions. And then my ingredients are lettuce, spinach, tomatoes, cucumbers, carrots, onions, bell peppers, avocados, cheese, croutons, chicken, olive oil, vinegar, salt, and pepper. My actions are that you can chop, mix, add, dress, and serve. I define the class for a recipe. Here's exactly how it is going to come out. I'm not a Michelin star chef. I don't know how to code the Python for a Michelin star recipe. If I did, I would do it. But so it's code for a recipe, and it's going to come out with something. And then here's again, it's all like you have to hard code all of the initial boundaries within it, right? So it's all math how exactly you want your mutations to work in every single individual aspect of the mutations, including all of the math for all of the ingredients, right? And then so we run all of our ingredients, and then here, my recipe is to take 0.97 units of chicken, 0.52 units of carrots, 0.78 units of tomatoes, 1.5 units of cucumbers, 0.97 units of lettuce, and then we serve, chop, dress, and mix. And so it's a cucumber salad. Okay. I mean, again, this might turn out good. I'm not a Michelin star chef, right? But I mean, like, here you go. Here's your salad. And then just pointing this out, right? And then, so within this and how this is operating, the last core concept that I want to break down and make sure that you understand within this is this concept of fitness versus softmax. And that's the most important distinction to me when it comes to evolutionary algorithms and swarm algorithms, as opposed to neural networks, right? Neural networks are heavily dependent on the softmax function. And then so what's the difference between these two? Fitness is a core concept in evolutionary algorithms, and it quantifies how well a solution performs relative to others. Solutions with higher fitness values have a greater probability of being selected for reproduction, ensuring that better performing candidates contribute more to the next generation. So it's a very probabilistic mechanism, and then it's based off of evolutionary aspects, rewards. It's how well the model is doing and the individual is doing compared to the environment, and the environment rewards and the environment structure. Softmax, on the other hand, is a mathematical function commonly used in neural networks and reinforcement learning. It transforms a set of scores or logits into probabilities by exponentiating the values and normalizing them. This makes it useful for selecting among multiple competing choices in a way that reflects relative confidence levels. So breaking it down into this, they're two very different functions, right? And that's what I want to highlight up front here. Like they do two very different things with regards towards how they work. Right? Like their end function is very similar, but they're doing two very different things on the back end, right? Extremely different things. And then so why evolutionary algorithms don't use softmax? One, it's a direct selection over probabilistic selection. So evolutionary algorithms operate by selecting individuals based on their fitness ranking rather than probability distributions. The highest performing individuals are naturally favored for reproduction without needing probabilistic transformations. You have probabilistic transformations within like that reproduction process itself, but you're taking always the strongest candidate, right? And then selection pressure is explicit. So evolutionary algorithms often use deterministic or semi-stochastic selection mechanisms like tournament selection, roulette wheel selection, or elitism. These approaches explicitly favor higher fitness individuals while maintaining diversity. Softmax would introduce unnecessary randomness, potentially selecting weaker solutions too frequently. So again, with fitness, we're programming out like the entirety of those initial functions, right? Like here's like a book, because here's your initial sequences, whereas softmax, here's your one line of code because everything is being just randomly generated. Softmax smooths differences, and evolution exploits them. Softmax tends to soften the contrast between different scores, meaning even weak candidates might get a chance, whereas evolutionary algorithms are the opposite. They thrive on preserving strong candidates, and they will go through and ruthlessly weed out weak ones very efficiently, maintaining a sharper selection pressure. It's like an exact opposite within that regard, right? Efficiency and computational simplicity. Evolutionary algorithms only require basic ranking and selection operations, making them computationally efficient, whereas softmax introduces exponentiation and normalization steps, which are not needed for survival of the fittest mechanisms. The key takeaway here is that evolutionary algorithms focus on survival and reproduction of the fittest, whereas softmax is useful when decisions require a smooth probability distribution over choices. Since evolution directly favors the best candidates, softmax is unnecessary and often counterproductive within this particular context. The last thing I'll note though within this and leave you on is that you can 100% absolutely, as a next step, if you wanted to, like create an evolutionary neural network, right, which would be possible. And then so your evolutionary neural network in the end would have a softmax function, right? So you would in that instance be combining the softmax function with the fitness function, and then that would be a perfectly viable model and it would work. And there's like companies that are based off of that research in that area, right? And then so you can do that and go and research in that direction and combine these things, right? There's nothing that says, okay, this is how this works and this only uses this, but there's nothing that says you can't combine A with B or A, B plus C. That's the beauty of this, right? And then it's all of these combinations and it's all systems complexity at the end of the day. Like, why do these systems work? They work because they're complex systems, because it's a bunch of soup, and if you throw a bunch of complex soup in there, eventually you get more complex soup. And then it doesn't necessarily matter what the exact measurements of the complexity are, as long as you're just tossing in enough complexity in there. And then so that's what it boils down to at the end of the day. Like this type of content, please like and subscribe. If you want further content, check out Rick's Cafe for deeper discussions. Thank you very much.